uh, electrical energy. So those things are not covered under. You can also have a onboard instrument to measure how much radioactive material, like you have the material on the surface of earth, particularly the crustal material, they constantly emit there is a constant decay of radioactive material, right? Like you have uranium, thorium, so potassium, so there is a decay of this material. There is a so that also can be measured by a onboard aircraft or aircraft normally. So they are not covered under remote sensing. They are covered under, that is something which is known as radiometric survey and geophysical survey and sound survey. These are all not covered under remote sensing. They are part of geophysical survey, right? So with these basic premises, we'll start our presentation today. Uh, okay. You can just raise your hand whenever you feel there is something to be asked. Whether the slide is visible?
Yes, sir.
Yes, sir. Clear, sir.
Okay. Now, uh, so these are the things which we will be covering: the definition of remote sensing, nature and source of electromagnetic radiation, that is what the light is, spectral distribution of emitted energy, interaction of electromagnetic radiation with matter, spectral regions useful for remote sensing. Not all regions are useful for. There are different regions of different wavelength range. Now, when I say electromagnetic energy, it's a it's a spectrum of energy, as we will be discussing subsequently. And as we discussed, no acquisition of information about object, phenomena, or processes without actually being in physical contact with them. So data is analyzed to obtain information. Now formation of image on retina of human eye. Eye collect part of EM radiation, visible light only, and information on retina is processed by brain. So this here in the retina, you have those photosensor, that is the rods and cones, which actually measure how much light has come, right? So these are the some of the standard definition by Lillis and Kafer and by Sabins. More or less similar definition have been given. I mean, the science and art of it's also known as science and art. Uh, can you tell me why it is known as science and art? Basically, the when you say art is something which science is something which can be programmed. I mean, you have a couple of assumption and make a theory, and eventually you come out with a result, right? But art is not exactly that. A scientific lab, a scientific experiment is can be replicated with a set of assumption. But in remote sensing, the interpretation part of it is quite often so complex that it is not amenable for normal algorithm based processing. Many things has to be interpreted based on the domain knowledge of individual. So people will interpret the same image differently. A geographer or a geomorphologist will interpret it in a certain way, a geologist will interpret it in a certain way, while an agricultural scientist or a let's say a forestry person will interpret in a different way. So you cannot have a comprehensive algorithm for everyone. So there is where the art of interpretation comes in. Now, as we discussed, the remote sensing exclude geophysical methods such as electrical, magnetic, gravity, and of course the measurement of gathering information through sound waves, right? Now, how it originated? I mean, the first remote sensing perhaps is I mean, in a from the point of view of replicating our the kind of remote sensing we do with our eyes with the instrument was through photography, right? Now, people used to send pigeons. Pigeons will be normally fitted with some small camera, and it used to say, take some photograph just to have photograph of a city, right? But the normal photography is again restricted to visible range in those days. And then, of course, you had initially it was a black and white photography because you have only one range of EMR and you have sensor. You have basically those are basically silver iodide, no? Those earlier photo film, if you remember, if you have seen, some of you not remember because none of you have come across those photography. In earlier days, there used to be a film which was normally exposed. They were basically silver halide, and silver halide is sensitive to light, and depending upon the exposure, a photograph used to be made in olden days. So that is how photography. So when you take such camera to air, then it's aerial photography. So initially, it started with pigeons, then with balloons, and finally with small aircraft. Right now, in 1970, actually, the technology was developed to acquire image in other parts of PMR. Prior to that, it was only in visible range that photography was being done. Uh, this is this is the time where uh, when the analog, I mean silver halide, was replaced with what is known as electronic sensor, or what is known as uh, solid state sensor, right? Uh, they are basically electronic devices, and each sensor is designed in such a manner that it can, I mean, when the light falls on those sensors, it creates an electrical impulse, right? Now, each sensor is sensitive to a particular range of EMR, right? So sensors are the solid state detector, or were charge coupled devices. They're basically known as CCD, charged coupled devices, right? Charge coupled devices were in those 1970s and those period, these sensors were developed. So they are capable of uh, the beauty of those solid state detectors uh, is they can uh, the light energy, when it falls on it, it creates a electrical signal, and electrical signal is uh, converted into a digital number. I mean, how much light has come, it can be measured uh, by the detector, right? And how much light, suppose you have three band detector. Now, which effectively means you have three different array of charge couple devices, right? One array means a rectangular array. I mean, you have thousand by you. All of you are using uh, camera, no? Our mobile camera, right?
Yes, sir.
Can anybody tell? Can anybody tell me what do you mean by resolution? There are two kinds of resolution in your camera. One is optical resolution, another is what do you mean by 1 megapixel? 1 megapixel camera. What do you mean by that?
So it means that there's which picture I can create. There's a 1 million pixel.
To have 1 million pixel in a picture, how much solid state detector you should have? The the sensor, you are having an rectangular array, let's say 1000 by 1000. 1000 by 1000 is 1 mega, no? Yes, 10 to the power 6, no? Am I correct? Are you able to get me? Hello?
Yes, sir.
Hello?
Yeah.
So when you say 1 megapixel, it effectively means your camera has, let's say, 1000 by 1000, let's say 1 million detectors. 1 million detectors which might have been squeezed into one square centimeter space. Can you imagine? And not only that, you maybe you need to have three set of detectors, right? One set of 1000 by 1000 detector capable of uh, telling you how much light has come in blue band, how much light has come in green band, and how much light has come in red band. Understood? So those many detectors have been squeezed into one square centimeter space in your camera. Are you able to get me?
Yes, sir.
So those, but this miniaturization of camera was not there in 1970. It took a lot of time. In those days, the initial charge coupled devices were very large, right? So that's the reason for you the remote sensing used to be very expensive, because the sensor designing used to be, each sensor used to be huge, right? Now with passage of time, the electronics and as well as the instrumentation has increased to such an extent that one square centimeter is also why one square centimeter, even one square millimeter can also accommodate 1 million solid state detector. Is it understood?
Yes, sir.
So, but it started in a very rudimentary way in 1970 when you have the capability to, you have sensors so designed that it can gather information in bands beyond the visible day, right? So that is the commencement of uh, multispectral sensor, hyperspectral sensor. So this is how it evolved, right? Now, all of you know about the light rays, no? About the electromagnetic energy. Now,
Yes, sir.
electromagnetic energy, it is modeled as a wave, right? Light passes through a straight line, but it has both an electrical wave as well as a magnetic wave perpendicular to each other, right? Now, light energy, as we see, it's an entire spectrum. The electromagnetic energy which comes from sun, it is an entire spectrum, right? Right from gamma rays to TV and radio signal, right? Now, gamma rays, ultraviolet, X-rays, ultraviolet rays, they do not reach the surface of Earth, right?
Yes.
Otherwise, none of us would have been here, right? A part of the ultraviolet ray managed to comes in when the ozone is relatively thin in some parts of the world, but these energy do not reach the surface of the Earth, right? But however, these energies, this is basically low wavelength. They have low wavelength and high energy. Gamma ray has much more energy. X-ray has much more energy than radio waves, right? Is it understood?
Yes, sir.
These are low wavelength, high energy electromagnetic energy. And then you have the visible range, zero point 0.4 to zero point 0.7 micrometer range. And then you have infrared microwave, TV, and radio waves, right? Now, these form of energy, this high wavelength energy can travel quite, right? Now, if you want to do remote sensing of, let's say, you want to watch how for the stars, what is happening in outer space, then you require a radio telescope. Understood? So, and of course, the radio signal, like what we have, our normal conventional uh, radio transmission, all it happens through in this range. Whereas microwave, like you have all our radar in airport radar, which in fact the landing and all that of aircraft is managed through this microwave range, because microwave is something which can penetrate uh, the clouds, so it is not affected by so this form of electromagnetic energy is useful for both remote sensing as well as for other purposes also, like as we discussed. No, you have you have radar for navigation, you have radar uh, for detecting signals, like all these defense people, they started using radar in the initial days of use, when particularly during the Second World War, right? So you can send signal, uh, but once somebody sends signal, it has to be the enemy party needs to check it. So they started also tampering with those signals. So how to gather that? So microwave is widely started they started using during the Second World War particularly, and of course the TV and radio was always it was already there, radio transmission through radio waves, right? Now, as we discussed, no, human eyes only measure visible light. Sensors can measure other portions of EML, right? Now, this is how the basic principles of remote sensing is. You can you can have an aircraft, or you can have a spacecraft. Now, spacecraft. Suppose a spacecraft, it gather information only in one band of EMR, right? Then you will have a black and white photograph, right? A spacecraft, supposing it gather information in the visible range, in near infrared, in far infrared, and yeah, in far infrared, let's say 3 bands in far infrared. Now, then you can have five, six, yeah. You can gather this information and make different combination. All of you know what a image, how a color image is made. All of you see a color image, no?
Yes, sir.
How a color image is made in your system. I mean, have you opened your any of your photograph in, let's say, in some of these normal photo viewing software, like image viewer, and have you gone through those things? Yes.
Yes.
Now, can you tell me, any one of you, can you tell me how a color image is made?
So when all the
Mm,
radiation is absorbed, only red are reflected, and I can see the red image.
Mhm. Anyone else?
There are three colors: red, green, and blue.
Mhm.
Its objects are the
Okay. So how it is made is, see, you have three primary colors, right? Or let's say three primary color gone in your computer, right? You see photograph in a computer screen, no, or in a laptop, or in a palm top, or in a mobile, right? So every instrument has electronic instrument has three primary color gun: a blue color gun, a red color gun, and a green color gun, right? Right? Is it understood?
yes, sir.
Now you gather information in, let's say you gather information uh, in zero point 0.4 to zero point 0.7 range, in zero point 0.7 to zero point 0.9 range, and 1.1 to 1.4 range. Let's say I have three different raster collected from three different ranges. Like one is zero point 0.4 to zero point 0.7, one another is zero point 0.7 to zero point 0.9, another is 1.1 to 1.4, right? So I have three different array of numbers, digital numbers, right? I assign a blue color gun to this, a green color gun to this, and red color gun to this. I get a color image. So a color image is basically combination of different three different raster. Have you heard of raster and vector?
Yes, sir.
Yeah. What is the basic difference, or what is a raster?
So raster have a pixels and vector diagram.
Raster is an array of
Raster is
numbers. A raster is an array. पता है ना array? Array मतलब ARRAY. Array means you have a a column and a rows, right?
the combinations
A
of
ras
pixels.
Yes, a raster is a combination of pixels or an array of. So what is that in pixel? Each pixel will have some numbers,
DN value.
DN value. Those DN value can represent anything, no?
Yes, sir.
Those DN value can represent population density. Those DN value can represent temperature. Those DN value can represent pressure. Like quite often you see, rasters depicting uh, uh, temperature anomaly on Indian Peninsula, let's say, right? So those DN value can represent population density also. I mean, you can show any kind of material in a raster, right? Any kind of information, right? In case of remote sensing, those DN value represent the amount of electromagnetic energy received in a particular range of electromagnetic spectrum. Is it understood?
Yes, sir.
So basically, when you have a color image, you have three different raster, right? And you are assigning blue, green, and red color gun to those three different raster. Am I am I understood?
Yes, sir.
Okay. Now, how data acquisition takes place? Now, as we discussed, now you have a source. Now, this source can be passive. In case of sun, it is passive. You can also have an active source. I mean, we can send signal and receive back the signal also. Like they call it light detection and ranging. You when light detection ranging, you send a signal and receive back the signal, right? You can also have what active microwave sensor. You can send a microwave and receive back the signal. So those are all known as active remote sensing. In this case, it is known as passive remote sensing, where the source of energy is sun, right? Now, sun energy, as we know it propagates through atmosphere, reaches the Earth's surface, and then part of it get part of it part of the energy gets into the earth. Gets into the earth means it heat up the earth. That is what I mean, right? Part of the energy heat up the earth, and a majority of the energy get reflected, and those things which get heat up the earth, no, eventually go out as emission, right? Understood? And
Yes.
now once, so supposing you are doing remote sensing of this area, you want to know what are the kind of material here. So as it moves through the atmosphere, it also get retransmitted. I mean, it comes here, it goes back, but while it comes to the atmosphere, it takes a variety of path depending upon it travel in the straight line. But then again, there are several obstacles. There could be clouds, there could be uh, particulate matter. So those things happens here also while it goes back. And if you have a sensor here, no, a sensing system like an aircraft, a high level aircraft or a satellite, as it goes through the entire atmosphere, it also, in addition to this information, there are other things also which get incorporated, right? Understood? There are what do you say, scattering of material. Those things we'll be discussing, right? So eventually you get the level of energy from this place, and in addition to this place, there are other things also which known as this is basically known as the amount of electromagnetic energy which get uh, or the total, what they say is energy flux, right? The amount of energy which comes from here, which get registered here, is a combination of energy going from here, as well as there are several other energy from the atmosphere which goes here. So it is known as a atmospheric scattering and other things, right? Now once the information is reached here, so you have, it creates a electrical signal, and those electrical signal can be processed to give you a pictorial output or a digital output, and eventually you get an array of raster, right? Depending, suppose you have only one band, you get one raster. If you have multi-band, you have multiple rasters. Now, to do this, to just a little bit about the physics of behind the electromagnetic radiation. Pure energy and pure mass are abstract concept only, right? Now, this is what the famous equation: energy is equal to mass into c square. C is basically the speed of light, right? So, which effectively means all the energy has come from mass, no? And the mass can be a form of energy. Understood? A mass also can be a form of energy, right? I mean, you can produce energy from mass, right? So everything has come from a vacuum up, and it can. That is the concept of E is equal to mc square. So you have a cluster of you have a vast uh, source of energy, and those energy condenses to form mass, and those mass also uh, can can be fused, can be fissioned to produce energy, right? So the easiest way to uh, do is fission. That is what the nuclear reactors are. I mean, you have the radioactive element which gives out. I mean, their uranium and thorium, the fission of which give rise to a huge amount of energy, right? So the now comes to the how it propagate, right? Electromagnetic energy has has both an it it moves in a straight line. The light moves in a straight line. C, if you remember, C is equal to 3 into 10 to the power 8 meter per second, the speed of light, right? So it moves along a straight line, and it can be modeled as a electrical wave as well as a magnetic wave. So that both electrical wave and magnetic wave are perpendicular to each other. So this is uh, the speed of light is equal to lambda. Lambda is basically the wavelength, right, multiplied into frequency, right? Frequency is how many cycles per second. I mean, this one particular wave, no, this is what they say is a sine wave, right? How many cycles? This completes one cycle, right? It's here, goes up, it's a peak, then you have a negative peak and comes back here. So this is one cycle. So how many cycles per second? That is what frequency is. So higher the wavelength, less is the energy, right? Lower the wavelength, high is the energy component in the light. So this is what wavelength and frequency. So two maxima, the distance between two maxima or one complete cycle also you can say, is what the wavelength is. Now high wavelength and low, this is low wavelength and these are the high wavelength. Now short wavelength are high frequency or high energy. That is, as we discussed, no, the lower end of electromagnetic spectrum, particularly the ultraviolet, gamma, X-ray, they are all short wavelength, high frequency, and high energy. Whereas the radio, microwave, they are all long wavelength, low frequency, and low energy, right? So higher the wavelength, lower is the energy level in the EMR, right? Now, there is another theory also of to describe the light. This is what particle theory. Uh, See, this basically gives an insight of into the interaction of electromagnetic energy with the matter. The it says the electromagnetic energy consists of discrete unit. I mean parcels. Discrete unit means they're parcels of photon is basically uh, I mean it's a parcel of energy, parcel or quanta, right? So these are all here the quantum of energy is this is by Planck's constant. Uh, so the amount of energy, I mean energy of a quantum or quanta, it is expressed in joule. Uh, how much how much energy is contained in a photon is basically dependent upon uh, you can calculate it from Planck's constant into frequency, right? So this is what the particle theory. I think these are all just to brush up your high school uh, physics knowledge. Now, so each quantum have mutually perpendicular electromagnetic vector, right? You have a in a in propagation, light propagation is along a straight line, but you have mutually perpendicular electrical wave as well as magnetic wave. So electrical and magnetic field oscillate in the form of sine waves. That is what we discussed. It starts from the baseline, then there is a positive peak, then you have a negative peak. So how much intense the light is basically depend upon number of quanta or amplitude of electromagnetic field, right? So all matter radiates electromagnetic wave depending upon its temperature, total wavelength range of a spectrum. So you have right from gamma to radio. So optical range is in this range only the optical law apply, right? The law of optics, that is reflection, refraction, it applies only in the ultraviolet, visible, and infrared range. So this is also known as optical remote sensing, right? Now, so in this spectrum, no, so as we discussed, now you have the ultraviolet, and beyond that you have the gamma and X-rays. So remote sensing is not done through in those ranges. So you have the visible range, zero point 0.4 to zero point 0.5, zero point 0.5 to zero point 0.6, 0.7 to zero point 0.6 to 7, and the how much energy comes, I mean, eventually comes to the surface of Earth, right? As you could see, from the entire the 80 to 90% of the energy that come from sun in the visible range get transmitted to the through the atmosphere and reaches us, right? And of course then it gradually decreases, and then the emission from Earth, the light, the energy that gets contained within the surface of Earth and heat of the Earth eventually get emitted, right? Now this is the curve of emission, right? No, this is the complete spectrum. As and which spectrum is useful for what? Like you have the cosmic rays, gamma rays, X rays, ultraviolet, visible, reflected infrared, thermal infrared. Now the exact range which normally see, these are all, these ranges are basically, we have given these names, right? The exact range that has been given we will be discussing subsequently. Now, visible is zero point 0.4 to zero point 0.7, and zero point 0.7 to uh, 3 micrometer is normally the reflected infrared. 3 to 15 micrometer is the thermal infrared, and then 1 mm to 1 meter is microwave, and beyond that it is all television and radio signal, right? So this is, as we discussed, no, gamma ray completely absorbed by the upper atmosphere, not available for remote sensing. X-ray also same thing. Ultraviolet incoming wavelength, anything less than zero point 0.3 get absorbed by ozone. Photo ultraviolet transmitted through atmosphere, but severe scattering detectable with film. Now we'll discuss what scattering is, and this is the visible range. Then you have the infrared range. Infrared, you have the near infrared or reflected infrared. Infrared interaction with matter varies with wavelength. Atmospheric windows are separated by absorption band. We'll discuss about those things. Then you have the thermal infrared, 3 micrometer to uh, 15 micrometer. But beyond that, in these ranges, remote sensings are not done, right? 14 to 100 micrometer remote sensing is not done. And then you have the microwave, zero point 0.1 to 1 meter. Longer wavelength penetrate fog, cloud, rain, and images are created by active as well as passive mode. Same thing is microwave is part of the radar. Microwave and radar, I mean, from the point of view of remote sensing, they're the same, right? So then, of course, you have the radio waves. No, have you heard of this absolute zero or 0 degree Kelvin? Excuse me. Hello.
Yes, sir. That's not possible, sir.
Yeah. Tell me.
Yes, sir. Yes, sir. We can hear you. So,
Okay.
please, anyone response? Sir is asking something.
Yeah, I'm just discussing about different laws that I mean, these are different principles through which the you need to understand these laws to interpret. I mean, to uh, not to interpret, but to understand what are the processes that takes place in remote sensing. Right now, sun is the most obvious source of electromagnetic radiation in for remote sensing. Right now, that is the source. Right, but it reaches the surface of the earth and earth get heated up, right? Now it's a question of even a even an object at minus 273 degrees centigrade can also emit electromagnetic radiation. That is what I wanted to tell you, right? This is 0 degree Kelvin. 0 degree Kelvin is minus 273 degrees centigrade. That also emits electromagnetic radiation. How much energy an object radiates is a function of surface temperature, right? And this Stephen Boltzmann law, it says how much energy, see total radiant exitance from a surface of of a material, right? That is total energy emitted is equal to this constant into temperature in Kelvin to the power 4, right? Now, how it is expressed? The energy is expressed in terms of watt per square meter at a particular temperature, right? Temperature expressed in the form of Kelvin. Kelvin is a scale, like you know, centigrade is a scale. Kelvin is also a scale. Now, spectral distribution of emitted energy by black body. Have you heard of something called black body?
Sir.
ब्लैक बॉडी के बारे में थोड़ा बहुत कुछ याद है आपको? ऐसे there is no black body on the surface of the
The
earth,
black
right?
body that absorbs
Black.
all light.
Yes, then no, it's not that way. It means it's a black body is a hypothetical. There is no true black body, right? Black body is a hypothetical object which emit all the energy that it receives. आप समझ रहे हो ना? Whatever energy it receives, no, the entire amount of energy it exits from the surface of the black body. Is it followed? No.
Repeat it.
ब्लैक बॉडी का जो कंसेप्ट है ना, it basically means whatever energy is received by that but hypothetical object, let's say from sun, whatever energy is received by the black body eventually exit the black body. So a black body is an ideal reflector. Understood? A black body is an ideal reflector. It's not that it absorbs everything. or we'll skip it and discuss it subsequently. If you're if it is not if you're not able to understand, no, we can skip it for now and discuss subsequently.
Yes, sir.
Okay. Okay. So this part we'll discuss, I think, when we take up subsequently the thermal remote sensing. Right? We'll discuss in detail about blackbody radiation when we discuss the thermal remote sensing.
Okay,
Is
sir.
it clear? Okay.
Okay, sir.
So two categories, that which falls on the earth and is absorbed, reflected, and that which is emitted by earth, right? Now, as we discussed, no, I think, is it visible? This yellow one, is it visible? No.
Yes, sir. Visible, but not so much clear.
Okay. Now, we'll be discussing about the passive remote sensing. You have the sun as a passive source of energy, then energy comes to the surface of earth and then gets reflected, right? This is a passive sensor. Uh, so then you can have an active sensor. So here the passive sensor receives energy from the earth energy, right? I mean, earth energy means, as we discussed, no, anything that is above the 0 degree Kelvin emits certain amount of energy. So those energy also can be, you can just measure it by any sensor, and how you'll get an idea of how much energy has come in thermal range. And you can also have an active sensor. You can send a signal and you can receive back the signal, right? Now, how it interact? I mean, when the light energy comes from sun, it is incident here. It is also incident. It goes in all direction. No. Now we're discussing about how much energy has come from here, right? How much energy has? Let's say you have an instrument here, the remote sensing instrument. How much energy it receives, right? Now, as you could see, when it comes from here, you have a variety of energy getting scattered and getting absorbed by the atmosphere and then goes to the sensor here. Some of the things also come directly to the sensor from sun. Some of it pass through the cloud, get deflected, and then gets reflected back. Now, there are some emission process, light energy which get contained on the surface of the earth and get heated up, no, finally get uh, finally gets emitted. Those things also goes to the remote sensing instrument. And then you have the atmospheric emission. So though you are trying to interpret this part from the energy that is received here, the energy that is received here is basically a combination of several amount of energy coming from different places, though dominantly going from here, but you also have several other energy coming from different parts which are not characteristic of this particular object, right? So there are ways and mechanism to deduct the influence of this material, right? So how it interacts? Electromagnetic energy are basically photons or the parcels of energy with momentum which travels with a momentum along a straight line. Intensity which with matter interaction with matter can change the following property of the incident radiation. When it when the light energy falls on a an object, it interact with the object, and in the process its intensity, wavelength, polarization, hello. Now a light, when it is polarized, you can have two waves perpendicular to each other, right? I mean, the it is basically vibration of particle, right? Now what do you mean by wave? Wave is basically vibration of of the energy, right? Now when you say a light is polarized, it means the vibration direction is in two perpendicular direction. Is it understood?
Yes, sir.
Okay. Direction, the direction of propagation of light, that is the direction. Now phase is you have the wavelength, no? Right? Suppose you have a longer wavelength and a shorter wavelength. So one full cycle is known as one phase, right? Understood?
Yes, sir.
Okay. So another wavelength light can be out of phase with a particular. So suppose you have two different wavelengths of light, no, they can be out of phase also. That is what it means, right? Okay. Now, how energy interact with the atmosphere? How the electromagnetic energy interact? Now, it interact with gases. You have nitrogen, oxygen, ozone, carbon dioxide, carbon monoxide, argon, water vapor. These are the gases. You have the particulate matters like smoke, dust. And then, of course, you have rock debris on the upper atmosphere, not atmosphere, sorry, in the you have asteroid belt, no? You have asteroid belt in the space. You know that you have a belt of
Yes,
asteroid, based belt of asteroid in a space. So they are basically rock debris, no?
yes, sir.
So light passes through that also. Light gets deflected from there also, right?
Yes, sir.
Okay. Now all radiation detected by remote sensor passes through some path length of the atmosphere, right? Now when a sensor detect the energy has traveled to the surface of the earth, reached the sensor. In addition to that, some of the energy has not reached the surface of the earth. It has gone from atmosphere directly to the sensor, right? And some energy has gone directly from the surface of earth in the form of emission, right? So you have different path length, right? You have different length of path traveled by the energy and eventually reaching the sensor. This is what I was discussing about, because it's not, it's simple reflection process that it is coming here and you have kept a sensor exactly uh, at a point where the reflected energy can be received. It's not that way, right? And atmospheric absorption and scattering is also one of the most important factors which needs to be taken into account while you study remote sensing, right? Now let's discuss about absorption, right? Now, spectral radiant emittance, right? How much energy get emitted, right? Acha. Can you see this top? Can you see this curve on the top?
Yes, sir.
This curve is basically solar irradiation curve outside the atmosphere. इसका मतलब है आपका you have energy right from gamma to microwave coming, no, from outer atmosphere आ रहा है ना वहां से. Let's here we are discussing about not the microwave. We are basically discussing about the from ultraviolet to higher infrared, right? So in this range, maximum energy, see, as you could see, very little energy comes to the surface. Out of that comes, this is solar irradiation, means how much energy comes to the top of the atmosphere, right? Understood? So top of the atmosphere also you don't have much of, you don't have gamma ray and all those coming here, right? Majority of the visible range light comes to the atmosphere, even to the top of the atmosphere, right? And then you could see a smooth curve. The higher wavelength, lesser and lesser amount of energy comes. Is it understood? Are you able to understand this curve? Tell me. ये समझ में आ रहा है? Hello.
If you have any confusion, you can ask, sir, to repeat that part. If you don't understand, then the whole process will be in a different way. So if you have any confusion, you can ask, sir.
इसमें दो कर्व है, एक ऊपर है एक नीचे है. Are you able to understand the top curve?
Sir,
Irradiation means solar energy curve outside atmosphere, means atmosphere, top of the atmosphere को how much energy has come in, and उसका x axis में आपका है wavelength up to 3 micrometer, right? 0 to 3 micrometer range में है. बोलिए.
sir, somehow is it possible to calculate the amount of energy that is reflected by the dust particle in the atmosphere from the satellite image, or through these two curves? Because one curve is showing the reflectance capacity top of the atmosphere, and another one is near the surface or above the surface. So is it possible to differentiate these two things, and from that differentiation, is it possible to identify the amount of particulate matter present in our
Yes.
air parcel?
Yes. Those are theoretically possible, no? That is how it has been made.
Okay.
These are all theoretical exercise by which it has been made, no? बोलिए. All of you understand now? Now, this curve denotes the amount of solar energy that reaches the top of the atmosphere in visible and infrared range. And as you could see, as you go to the higher wavelength in the infrared range, lesser and lesser amount of energy is received. This part is understood?
Yes.
Okay.
Yes, sir.
Now, then when you come to, now this is the amount of energy which has come from sun and which has reached the sea level, right? Now what is there between sea level and top of the atmosphere? It's the atmosphere, no? It is the atmosphere, agreed? सी लेवल एंड टॉप ऑफ द एटमॉस्फेयर के बीच में है क्या? एटमॉस्फेयर ही तो है,
Yes, sir.
right?
Yes, sir.
Yes, sir.
Yes, sir.
Now you see in the visible range also there is a gross reduction of solar energy coming to the let's say coming right up to the sea level, right? Okay, it has been reduced, but at the same time there are certain places where there is a sharp reduction, like 0.78 perhaps, right? 0.95, then 1.1, 1.4. Can you see? Then 1.8. See, these are all sharp reductions. So, like here, if you want to design a sensor for land-based studies, see, almost the whole part of the EMR is being eaten up by the atmosphere, right? By the water vapor and carbon dioxide, right? Here it is being absorbed by the water vapor in the atmosphere. Here it is being absorbed by water vapor in the atmosphere. Here the energy is being absorbed by oxygen and H2O. Here this sharp decrease in the visible range of energy also is due to ozone, right? Now this can be computed. These are all computation, theoretical computation, which has been validated also, right? Now if you want to do remote sensing of Earth surface, you cannot have any band in this part. But if you want to do remote sensing of cloud is a combination of carbon dioxide and water, no?
Yes.
If you want to do remote sensing for cloud, you should have a band here. Is it understood?
Yes, sir.
Okay. So with this, we'll come to the atmospheric transmission, that is how much energy comes to the surface of the earth, and the concept of atmospheric windows, right? Now as we saw in the last curve, no, now we'll be seeing for the entire visible infrared and thermal infrared as well, right? Now this curve is basically atmospheric transmission, right? Now if the energy is 100, no, coming from to the top of the atmosphere, now let's say the energy that come to the top of the atmosphere is 100, right? Let's say this is 100. Understood? Is it followed? Whatever comes to the top of the atmosphere, let's say this is 100, right? 100%. Okay. Followed?
Yes.
Okay. If whatever come to the top of the atmosphere is 100%, then almost 90% of the light in visible photo ultraviolet, like 0.3 to 0.4, and near infrared, right? Apart from some of these absorption, a majority of the light reaches the surface of the earth. 90% of the energy reaches the surface of the earth, right? But then there are sharp absorption due to water vapor in 1.1, 1.4, 1.8, right? Then 2.6, right? Then 5 to 8, right? So you don't do remote sensing in these ranges. These ranges are 5 to 8 is opaque to, I mean, though no information is reaching the surface of the earth, no? Is it understood? So surface land-based application, for land-based application, you should not have a band between 2.6 to 3, right? You should not have a band between 5 to 8. So this is known as atmospheric window. I mean, wherever you are having more than 80 to 90% transmission, no? Like these are all atmospheric windows. Atmosphere acts near transparent in this range of electromagnetic radiation. Excuse me. Okay, so if you see a normal color photograph that you have has three bands, one in point 0.4 to point 0.5, point 0.5 to point 0.6, point 0.6 to 7, right? You can also have a aircraft infrared photography. You can have 3 to 5 micrometer range, right? You can have infrared color photograph in green to infrared range photo, Landsat multispectral scanners. You have then you have the Landsat thematic mapper spot. There are many. Whether some of you have registered in and then the expanded version like infrared and microwave and radio. Now, as we see here, no, the X band, C band, S band, L band, these are all radars, right? I mean, this terminology started developing during initially X, C, S, L. They started developing during the Second World War, and since they were very much entrenched uh, in the literature, subsequently when the aircraft were designed for collection gathering of data in microwave, so those bands were also those nomenclatures also retained. So these are some of the radar satellite or microwave satellite, right? So this part we have discussed. Okay. Now with this, if it is understood so far, we'll have a little bit of discussion about what we say scattering. Anything you would like to ask?
No, sir.
Okay. So should I continue?
Yes, sir.
Now we need to know what happens to the electromagnetic energy when it interacts in the atmosphere, right? Now, one of the major things that happens is scattering of light, right? Scattering of radiation by atmospheric particles leads to, it can lead to change in frequency, intensity, direction, and distribution, right? Now, this has an adverse effect. There is a contrast reduction, skylight, change in spectral signature of the ground object. See, you are not, see, which effectively means when you, though your ground pixel, you know, there is a sensor, the amount in sensor you have in the sensor in the satellite, you have a certain uh, detector which is measuring a particular part of the earth surface, that is known as ground pixel, right? Now when you have scattering, in addition to the information that is going from ground pixel, you also have information coming from the atmosphere itself. So this creates a combination of signature. So this has to be excluded when you really do interpretation, right? Now, what are different scattering? Scattering depends upon the size of particle and the wavelength of the light. I mean, light is basically a spectrum, no? Which wavelength of the light will get scattered in how, in which manner, depends upon the size of the particle which is scattering, right? How much abundant the particle is, and distance of radiation path, right? How much path the light is traveling, right? Now there are different kind of scattering. One known as Rayleigh scattering is basically a molecular scattering. I mean, gas molecule. Your atmosphere has a lot of gases, like you have nitrogen, you have carbon dioxide. So molecule of those gases also do what you known as scattering, right? Now here the size of molecules is much less than the wavelength of light, right? Okay, understood. So in this case, what happened, the shorter wavelengths gets more scattered than the longer wavelength, right? And this leads to atmospheric haze, right? Now shorter wavelength means the blue light will be more scattered in comparison to the red light, right? There are two kinds of scattering: selective scattering and non-selective scattering. Selective scattering is dependent upon the size of the particles, right? Now particle could be molecule, particle could be dust particle, it could be cloud also, right? Now here in this case, the lesser the wavelength, the higher the scattering. Is it understood? In fact, Rayleigh scattering is inversely proportional to the fourth power of wavelength. Is it understood? Are you able to follow? Hello?
Yes, sir.
So, if the wavelength, I mean, which light will get scattered more? Right. Rayleigh scattering happens when the size of the particle, in this case it is molecule. Molecules are definitely naturally much smaller in size in comparison to the wavelength of electromagnetic energy. But here again, the lesser the wavelength, the higher and higher is the scattering, right? And the scattering is to the inversely proportional to the fourth power of wavelength, right? So, which effectively means the blue light will be scattered much more than the red light, right? So when the light passes through the atmosphere, the blue light gets scattered much more than the red light. Understood? And this is the reason why the sky looks blue. Is it understood?
Yes, sir.
And this is also the reason why the sky looks red during morning and evening, right? Now what happens, can you see here? This is a daytime. Now you have all the spectrum of light, not just BGR. BGR is something which you are able to see, other you are not able to see. No, so let's discuss about only BGR, blue, green, and red light. Other things, in any case, we won't be seeing, and we won't have any visible impact on the. I mean, we won't be able to see those light and its impact on the atmosphere, unless, of course, we are doing a remote sensing image, right? So our eyes can only see these three range of light. So what is happening is, in the daytime, as you could see, green light more or less pass with minimal scattering, but since the amount of Rayleigh scattering is directly proportional, sorry, uh, inversely proportional. I mean, lesser the wavelength, higher is the scattering. No, is inversely proportional to the fourth power of wavelength, right? So what is happening here is the blue light is getting scattered much more than the green and red light. So anybody standing here will see the sky as
Blue
red,
light.
right? On the contrary, what happens in the evening and morning is, now if evening you are here, no, you are somewhere standing here, and this is the horizon, no, so you are standing here, right? Now red light, see, everything gets scattered, it's not just the blue light, right? So red is also gets scattered, right? And blue also gets scattered much more than the red, right? But the red travels through a much longer part of the atmosphere. So though here things look blue, this part of the sky looks blue, this part of the sky looks red. Understood? Anybody standing here will see this part of the sky looks red. So this is the uh, bright red of morning and evening is due to Rayleigh scattering, because the red light travels to a longer distance in the atmosphere. Okay. This is also a reason why this is known as Tyndall effect, right? You have the ambient white light having uh, blue, green, and red light. It passes. You have colloidal particles less than 1 micron, so it passes through. I mean, it interacts. It gets scattered by this particle. Eventually, you see the light as you see the sea, particularly when you travel in sea, or any for that matter, any standing water body, you see them as blue, right? The next one is mice scattering. Mice scattering takes place when it is basically due to atmospheric particles, when the wavelength of light, and those range of light will get scattered when the wavelength is more or less same as the particle, right? So it is restricted to the lower atmosphere with water vapor and dust particles. Amount of Mie scattering is greater than Rayleigh scattering, and wavelength scatter are larger. So this basically is the cause for overcast condition or smog. you can have also have a particle non-selective scattering when the particle size is much larger than wavelength, or particle, I mean, then it becomes independent of wavelength. All the light gets scattered in a similar fashion, right? Let's say you have a huge amount of water vapor, right? Now the particle size, you have dust in the water vapor, you will have a lot of dust and dust particles. There what happens, the amount of scattering gets independent. It's a non-skeletic rate. All the lights get scattered in the similar fashion, and this is one of the, when you have atmosphere is heavily moisture laden and dusty, then you have, when all the visible light get equally scattered, you see the cloud was white, right? You see a white cloud. In this case, since the cloud is full of water vapor and dust, and they are much larger in size than your visible light, all the light gets scattered in a similar fashion, leaving to, so you receive equal amount of blue, green, and red light, so you see a ambient white, right? At sometimes when it is uh, when you have lot of water vapor and lot of dust particles, you receive less and less amount of blue, green, red, giving you a dark cloud. Is it understood? Is it understood?
Yes,
When you
sir.
have more and more of moisture, no, water is an ideal absorber of EMR. Is it understood? So if you have more moisture in the cloud, see, cloud is not always full of moisture. No, if you have a rain laden cloud, if you have lot of moisture in the cloud, then a majority of the electromagnetic spectrum is gets absorbed by the cloud in visible range, visible and near infrared range. So whatever reaches you is minimal. Since all these things, all the visible range of light gets absorbed more or less equally, you see a dark cloud, right? Now some of the deleterious effect of cloud is, now cloud, what it does is it sends a radiance to the sensor also. From here also this sensor, though, since you have a cloud here, now information from this part do not go. You have a shadow zone here, right? So the whole thing is a shadow. So you don't get any information about this object. And then if you get some information about object here, but in addition to the information from here, you also receive some information from here, right? And this energy, the visible range, sun energy, but invisible and near infrared range, is not able to penetrate here. So you have a complete shadow zone. So this is one of the reasons why microwave remote sensing is so important for quick assessment of flood and all that, because when you have a major flood, no, the invariably those area will be having a lot of clouds, right? I think we'll end with this. Otherwise, we'll end with this now and take up the class again on Tuesday. I'll let you know the time exactly, whether it's will be in the morning or in the afternoon session. So anything regarding this, if you want to ask, you can go ahead.
So if you have any question, you can ask, or if you have any clarification, then you can ask us. Sir, if you have some study materials on this topic, sir, and if you can share it with the students, I think that will be much better, because they will go through the materials and your lecture that they have wrote down during your lecture. And if they gone through both of these, then I think there may be some question that will arise from their study that they can
There are
ask in the next lecture.
some I think some old study material of Training Institute. I think I had given it to Sujay also.
Yes, sir.
Let me check if it is there. I'll send it to you.
Okay, sir. If you,
Uh,
I think the materials is with Sujay sir, but if you have the soft copy, then you can share it.
no, I do have the soft copy somewhere. I'll send it.
Okay, sir.
And what are the books students are studying from remote sensing?
I think sir they are basically reading Lillysent, the remote sensing fundamentals of remote sensing by Lillysent, and Janssen and Johnson.
Jensen and Jensen is a very good book.
Yes, sir.
You have that book?
Yes, sir. We have some copy in our library.
Okay, that is the best perhaps. Lillis and Kiefer used to be pretty good. In fact, it is the one of the classic you can say. But of late, Jensen and Jensen has incorporated a lot of new the modern concept of digital image processing into it. So, if all the students have access to those books,
Yes, sir. They
then
can brought it from the library.
okay, all the
Even
students
sir,
are resident
no, sir.
in the
They are day scholars, sir.
okay, but there are regular classes going on. No? Not
Yes, sir.
everything is off online,
No,
right?
sir. Now our department are running 5 days offline classes.
Okay, fine, fine.
Even sir,
So
I have seen a book, Physics of Remote Sensing. I forgot the name of the writer. Uh, that may be helpful for them.
no, it won't see such details won't be required at this
Okay.
juncture. They can do it subsequently. But for physics of remote sensing, Lillis and Kiefer is also pretty good.
Okay.
So they can uh, Lillison and Jensen will be both will be quite sufficient. They do not have to go for any other book. But there are some well, concise compilation. You can say it's not exactly. It's a study material taken from different books also. So which was compiled by the GSI Training Institute. I am going to send it.
Okay, sir.
Okay. Now, meanwhile, I would prefer the classes to be at least some interactive, unless there is some answers or some. Otherwise, it is difficult to know whether anything you are able to catch or not. So, please try to be more interactive in the subsequent classes. We're just ending with scattering. We'll take it off again from s- uh, from scattering, and then we'll discuss about the sensors and platforms how they're made, right? So I'll let you know on Tuesday, Monday. The class will be on Tuesday. Whether it will be in the forenoon or afternoon, I'll let you
Okay, sir.
know. Okay.
Okay, sir.
Okay then. Thank
ওকে
you.
থ্যাংক ইউ ভেরি মাচ। আচ্ছা, বাকিরা কেউ একটু লেফট করবে না, একটু থাকবে। আচ্ছা, স্যার লাস্ট যেটা বললেন সেটা আমারও প্রথম কোশ্চেন, যে তোমরা কেন কেউ রেসপন্স করছো না? যদি বুঝতে নাও পারো সেটাও তোমরা বলো। যদি এমনই হয় বুঝতে পারছো না কিন্তু কোনো কথা বলছো না, তাহলে তো কোনো লাভ হলো না ক্লাসগুলো করিয়ে, না? অ্যাটলিস্ট বোঝো বা না বোঝো, যদি না বোঝো সেটাও ক্লিয়ার করো স্যারদের থেকে, তাহলেই তো বেনিফিটটা পাবে, নাহলে পাবে কিভাবে? পার্টিকুলারলি দু একজন ছাড়া কেউই কোনো রেসপন্স করছে না, আদৌ তোমরা জেগে আছো না ঘুমিয়ে গেছো সেটাও বোঝা যাচ্ছে না। নেক্সট দিন থেকে একটু রেসপন্সিভ হওয়ার চেষ্টা করো। ঠিক আছে, লেট করতে পারো।
ঠিক আছে স্যার, স্যার রাখছি স্যার।
হ্যাঁ ঠিক আছে।